Hello, welcome to my channel. So in this EMF video on vector calculus, I'm gonna talk about a very interesting and a very important theorem. It's called Helmholtz theorem. So Helmholtz theorem is a fundamental result in vector calculus that states that any vector in 3 dimensions, say it's a vector A, so if it fulfills the conditions, so the conditions are a vector that decays sufficiently as it tends to infinity for a vector field defined on an infinite domain. If a vector sufficiently smooth, a vector is differentiable in its domain. If a vector is bounded within a domain of interest, then the vector field A can be uniquely decomposed into two distinct components. So mathematically it is represented by, the vector can be represented by two distinct components. One is curl free, which is called curl free part, and the other is curl of another vector, so which is called the divergence free part. So any vector that is that fulfills the conditions stated here can be uniquely decomposed into two distinct parts. It's very important in understanding EM fields and electromagnetic waves. It's really interesting. So where V is generally scalar, it can also be a vector. V is vector, which implies that this decomposition of a vector implies that any vector A, provided it fulfills required conditions, any vector can be completely understood in terms of how it diverges and how it curls, and vector A can be decomposed into a rotational or conservative part and a solenoidal part. So this theorem overall a very easy to understand theorem. It's like vector components of a vector. Like we decompose a vector in coordinate systems. Like in Cartesian system, we decompose vector, say r into ax, ay, az component, or sorry, rx, ry, rz component in 3 dimension. So like that we can decompose a vector field in two distinct components, which one of which is curl free and one of the other is divergence free. So this theorem helps us understand the behavior of electromagnetic waves in 3D space for all practical purposes. So all the practical in application, all the waves, radio waves, microwaves, all the plane waves, all the used, encountered, manipulated waves we see in our practical life in engineering. So all these waves satisfy or all these waves abide by Helmholtz theorem. Okay, so all the practical EM waves can be described, their behaviors can be analyzed according to Helmholtz theorem. So this is a very easy concept, and it's very powerful concept to fully understand, or at least understand at required levels, and very comprehensive tool a very useful concept in understanding electromagnetic fields and waves in 3D space. Given EM fields conform to this theorem, we can also describe an EM field in terms of Laplacian. So there is a relation in Laplacian that I want to tell you. Any vector that is described by Helmholtz theorem has a Laplacian that satisfies a certain relation. I'm going to show you that relation. Then I'm going to take some examples, simple examples. Then I'm going to show you some fields and how are they decomposed in distinct parts, and it's very interesting. So here, given any vector field A conforms to Helmholtz theorem, which is the mathematical expression of which is this. So the decomposition of the vector A in two distinct parts. So given divergence of that vector A is equals to a source density rho v, and curl of the vector equals to rho s, which is circulation density. Any vector field A has a Laplacian that satisfies the relation, this relation. So in my previous video I have discussed about Laplacian of scalars and vectors. So a vector field's Laplacian can be understood in terms of volume flux density, which is rho v, in this case I have designated, and its surface circulation density, which is rho s. And this relation fits within the framework of Helmholtz theorem. So this demonstrates the flexibility and utility of Helmholtz decomposition in various electromagnetic concepts. So in my upcoming videos I will discuss about electrostatics, electrodynamics, magnetostatics, magnetodynamics, EM waves. So understanding the electromagnetic waves in terms of vectors, in terms of fields. So understanding these somewhat abstract concepts which are used in electrical engineering as a basis. So it will this theorem and the related relations, mathematical relations and expressions will help us to solve problems and understand basic basic concepts in electromagnetics, and it will be very helpful for us if we understand how a field works, if it's static field, if it's a dynamic field, if it's a time varying field. So it's a very important tool, Helmholtz theorem and also Laplacian, and along with other vector calculus theorems and methods. So if we take an example, so also can be called the Poisson's equation. So if we take the example of this Laplace relation in terms of electromagnetic fields, so say examples. So there are various examples, like for scalar potential. So for scalar potential, so scalar potentials, this relation gives So Laplacian VE. So this is scalar electric potential. I have discussed this in my Laplacian video also. So it is the divergence of the electric field intensity, which is a vector, um, which is rho v by epsilon, or this is in general. So rho v is volume charge density or source density, and for vector potentials, it is, so A, Laplacian of A. So here this A is vector magnetic potential. So this is described by B, which is magnetic flux density, magnetic flux density is curl of the magnetic vector potential. So curl of A, which is mu J. J is surface current density, which conforms to this rho S. For EM waves, so EM waves, so Laplacian of electric field is mu epsilon O, partial differentiation 2 times of the vector field E, and magnetic wave. So in conjunction to electric waves, the magnetic equation, so which is also mu epsilon O, partial differentiation 2 times of the field itself, magnetic field itself. So these two equations combined form electromagnetic waves we encounter in engineering or our everyday life, though many of us don't realize it. So I have given the example of the relation of that any under Helmholtz framework, any vector A has a Laplacian that satisfies this relation. These are the examples. So if I take the example of this relation, that any vector that satisfies certain conditions can be decomposed into two distinct components. In terms of EM fields, examples can be shown that. So I have shown you the examples on this relation of Laplacian of a vector under Helmholtz theorem. So if we want to see the decomposed form of electric fields and magnetic fields separately by Helmholtz theorem, it will look like this. So for example, electric field can be decomposed into two parts. Electric field can be decomposed to two distinct parts, so which is this and TA. So this is the decomposed form of an electric field. So this is curl phi. So electric field can have both curl free or irrotational component and at the same time divergence free or solenoidal component. Solenoidal component. So electric field can have both parts, but when it comes to magnetic field, 0. So magnetic field only has so magnetic field only has the divergence free component. So it's always the case for magnetic fields. So if we observe it carefully, so magnetic fields are generally generated by currents and has no source or sinks. So there's no divergence or convergence in magnetic fields. So the resulting field is always no curl free or irrotational part. There's only solenoidal part, divergence free part. But electrical field on the other hand has a source density part and also a circulation density. So in terms of time varying case, electric field can have both irrotational part and solenoidal part. So this is all I have for today on Helmholtz theorem. So I will show you some I will visually show you the fields, electromagnetic fields in terms of Helmholtz theorem, and that will be it for this video. So here are 4 types of field representations or mappings of vector fields. So from the concept of vector decomposition, vector field decomposition, we can say that this field, say all the fields we are denoting them by A. So in this case the vector field A has it is solenoidal, so it isn't divergent or convergent. So in this case divergence of the vector field is 0. Also it isn't rotating. There's no local rotation, so this also doesn't have rotation, so its curl is also 0. So the curl free part is also 0 and divergence free part is also 0. In this case the vector field A is divergent from point, say P. This is P. So we can easily see that it's diverging, going outwards. The flux is outwards from the point P. So the point P is source, you can say source of this outward flux. So there is some value, say, which is source density, so rho v, and it's not rotating. There's no local rotation in this field, so it has no circulation, so 0 circulation. So in this field representation, this mapping, so the vector A isn't converging or diverging, converging to a point or diverging from a point, say P. So it is not divergent. This vector field A isn't divergent, so divergence is 0 and the divergence free part, the curl, there's local rotation uh, through the surface of this vector field. So there is obviously curling of the vector, so there is circulation. And in this case, say there is point P, so we can see that the vector A is divergent. It's emanating from a point, a source, so it is divergent, so it has some value. And the divergence of this in this case of this field has some value. And also there's local rotation, circulation to the surface. So there is also curl of there is also curl present in this case of the field. So there is rotation, there is circulation. So in terms of vector fields, we can easily determine a behavior of a vector field, especially in case of electromagnetic fields and waves. And if a vector is divergent or not, if it has circulation or not, if it has both. So this is very useful theorem, Helmholtz theorem, the concept of decomposing a vector in two distinct parts. So I hope you understood my explanation. I am really trying my best. These topics are little comparatively more abstract, and it's technical. It's quite challenging in general case comparatively, when we compare with other electrical engineering topics, but it can also be relatively intuitive and easy to understand also, if we just try ourselves. So that's it. Thank you. I hope you understood my explanation. If I have done any mistakes, you can tell me. And if you understood my explanation, please like my video, subscribe to my channel, share my videos. And I'm trying my best to discuss and explain these concepts. And thank you for watching thus far.